Hi guys, today we're looking at the chapter Gravitation. It is the 8th chapter of the physics syllabus of grade 11 Cbse. This chapter deals with how what goes up must come down, how planets orbit the sun, how rockets fire off the earth, and why astronauts don't feel their weight. Let's roll! Now, this is the mind map that we are going to be using to talk about the chapter Gravitation. Mind maps are very easy tools for us to understand what is important in that chapter. So this mind map is divided into 10 portions. And for your convenience, we will be expanding each part in order for us to explain what is in there and in order for you to read what's out there. So, gravitation. This is the 8th chapter in your physics syllabus, and it talks about Kepler's law of planetary motion, the 3 laws created by Johannes Kepler. And then we'll talk about Newton's universal law of gravitation, the universal F is equal to G m1 m2 divided by r square law created by Sir Isaac Newton. Then we will be looking at characteristics of gravitational force, the force that Newton founded with the law. And then we'll be looking at acceleration due to gravity and its variation with respect to height and depth. Then we will be moving on towards gravitational field and potential. And then we will move on to satellites. And we will move on to some formulae regarding escape speed, orbital speed, etc. And then we'll move on to the types of satellites such as geostationary satellite, polar satellite. And then we'll move on to the last topic, that is weightlessness. So let's move to the first topic. From gravitation, we move to Kepler's law of planetary motion. So these 3 laws are the Kepler's 3 laws regarding planetary motion. These were found by Johannes Kepler after 16 years of investigations of his master Tycho Brahe. Now these 3 laws are thus. The first law is the law of orbit. It states that every planet revolves around the sun in an elliptical orbit and sun is at its one focus. Now this says that the orbit of the planets around the sun is an ellipse, which is a closed curve with 2 foci. Foci being the plural for focus. Now a circle would be a special kind of ellipse having only one focus, that is the center. Now an ellipse, instead of a radius, has a semi-major axis, which is the distance between the center of the ellipse and the periphery. In the orbit around the sun, the planets move in an elliptical orbit while the sun lies at one of the foci. Now let's move on to the second law, the law of area. The radius vector drawn from the sun to a planet sweeps out equal areas in equal intervals of time. Now in a formulaic form, it is given as derivative of A with respect to time is equal to angular momentum divided by 2 into mass of the body. Now these 2 values are said to be a constant. Now this law explains why in an elliptical orbit, when planets move farther away from the sun, they tend to move slower, and when they come towards the sun, as in nearer to the sun's focus, they move faster. The difference in time being to compensate for the equal area that's drawn out. Now, the third law, the law of periods, is very important. This is found in most numericals, and it states that t square is proportional to a cube. Now here t refers to the time period of one orbit of the object around the sun, and a is the length of the semi-major axis. So this law says that the square of the time period is directly proportional to the cube of the length of the semi-major axis of the orbit. So this law will help us to find out time period and the length of semi-major axis of the orbit of any body around the Sun. So that completes Kepler's laws of planetary motion. Now, from Kepler's laws of planetary motion, we swoop around to Newton's universal law of gravitation, the law that Newton made up after he found the physics behind an apple falling from a tree. That's part 3. Let's expand it for you. Now, Newton's law of gravitation, the universal law of gravitation, states that when two mass bodies are separated by a distance, they experience an attractive force, which is directly proportional to the product of their masses and inversely proportional to the square of their separation. Now, as a formula, it is given as F is equal to G into M1 into M2 divided by R square. Now, F here stands for gravitational force. M1 and M2 are the masses of two separate bodies in the solar system, be it anywhere. R stands for the distance between the two bodies. In this formula, we square the distance. And G is referred to as universal gravitational constant. Now, the value of this universal gravitational constant was found out by Sir Henry Cavendish. And he found that G was equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. Now, this formula is very important, and you should be learning this in your derivative, in your derivations, as well as the formula itself, for it's asked to be applied in many of your problems. Now, from Newton's universal law of gravitation, we are moving to characteristics of gravitational force from 3 to 4. Let's expand it. So, now we'll learn about some interesting facts about gravitational force. Do you know that gravitational force is the weakest force in nature? That's right. We can easily defeat gravity by holding a glass stationary on a table down to our lips. There, I've defeated gravity. So that's why it's known as the weakest force in nature. So because of it being the weakest force, it's also a very long-ranging force. It can happen between two bodies anywhere in the universe. The second law states that it is central as well as a conservative force. Now, these are two very important terms, and you must have learned them in the first chapter. Now, let's revive it. Central means that it acts along the position vector. So if you have the moon orbiting around the Earth, the gravitational force is acting along the position vector, that is, along the distance between the moon and the Earth. A conservative force is a force which does not depend on the path taken. So you can take a body from another body and move it in a straight line or in a zigzag manner, but still the gravitational force will still be the same because it's a conservative force. The third characteristic of gravity is that gravitational force is always attractive in nature. Whenever there are two bodies, gravitational force always tries to bring them together. Now, this is a unique property of gravitational force because there are other forces like electrostatic force, which are attractive, but they also are repulsive. Now, the fourth characteristic is that gravitational force is applicable for all bodies, irrespective of their shape, size, and position. So gravity can act between any two forces. It can be, for instance, between your glass of water and a mug of water, or between your pen and your notebook. Those two have gravity in between them, but they are very feeble. This also is the reason why you cannot escape from gravity anywhere in the universe. So, with that, we've completed the characteristics of gravitational force. Now, we will move on to acceleration due to gravity. Now, you found out gravitational force. Suppose you need to find out the acceleration. You divide the formula for gravitational force by mass, and you'll get the acceleration due to gravity, which is represented by g in small letter. Now, the acceleration due to gravity is a very important quantity because it is usually used in our day-to-day situations. It is also very important in your numericals. Let's read out this statement. Acceleration due to gravity is the acceleration possessed by an object during free fall due to the Earth's gravitational pull. If I have a pen and I drop it to the floor, it experiences acceleration due to gravity. Same with the plane landing at the airport or a satellite orbiting the Earth. Now, g can be calculated in the following way. The formula here states that small g, or acceleration due to gravity, is equal to capital G me divided by re square. Now here, capital G stands for universal gravitational constant, me stands for mass of the Earth, and re stands for radius of the Earth. Now, in your earlier chapters, you would have known that the value of gravitation acceleration due to gravity is 9.8 meters per second at the surface of the Earth. However, in this chapter, you're going to learn the different values for acceleration due to gravity. Therefore, that value becomes non-existent. Now let's move on to the variation in acceleration due to gravity. Acceleration due to gravity varies in the following ways. Suppose from the surface of the Earth, you move up by a height h. The acceleration due to gravity that you experience would be lower than what you experienced on the surface of the Earth. The new acceleration due to gravity at a height h is equal to the product of the acceleration due to gravity g at the surface into 1 minus 2h by re. Now, h is the height that you've gone from the surface of the Earth, and re stands for radius of the Earth. So, g dash will be equal to g into 1 minus 2h divided by re. So, this shows you that gravitational force and acceleration due to gravity decreases with height. Now, let's see what happens in the opposite case. Suppose I drill down deeper into the Earth. What happens to the acceleration due to gravity? Again, it decreases. Let's see why. The formula here states that g dash, the acceleration due to gravity at a depth d, will be equal to the acceleration due to gravity at the surface, g, into 1 minus d by re. D is the depth that we have gone down into the Earth, to the center of the Earth, and re again stands for the radius of the Earth. So these formulas show you that the variation in acceleration due to gravity when you're going up from the surface of the Earth or going down from the surface of the Earth, it always decreases. Now, the third case here is the variation in acceleration due to gravity with rotation of the Earth about its own axis. Now here, g dash is referred to as g minus r omega square cos square lambda. Now here, g dash refers for the new acceleration due to gravity. The original g stands for the acceleration due to gravity at the surface, the 9.8 value, or the value in the earlier formula, g is equal to gm by r square. And r stands for the radius of the Earth. But what does omega stands for? Well, omega stands for angular velocity of the Earth's rotation. And the angle lambda stands for the angle between the equator and the latitude of measurement. Now we'll take two cases here, the ones at the poles and the ones at the equator. At the poles, the value of lambda is equal to 90 degrees. Therefore, cos theta, therefore, G has the maximum value. But at the equator, the same value of lambda is at 0 degrees. Therefore, G is at its minimum value. So even if we're at the surface of the Earth, the acceleration due to gravity changes as we move from the poles to the equator and back to the poles again. Now, these three formulae can be derived, but as they are very important because these three formulae are used in most of your problems in the chapter gravitation. Now, let's move on to the next topic. Topic 6 deals with gravitational field and potential. The gravitational field intensity deals with the intensity of the gravitational field around a certain object, say the Earth. Represented by the letter I, gravitational field intensity can be calculated as Gm by r square. Now G stands for the universal gravitational constant, m stands for mass of the object, and r square stands for the radius. Say the radius of the Earth if you're calculating for the Earth. Now, gravitational potential. It is defined as the work done by an object divided by its mass with respect to another object. It's represented by Vg, which stands for potential of gravitation. And it is represented as minus capital Gm divided by r. Again, G stands for the constant, m stands for mass, r stands for radius. But what does this minus indicate? Well, the minus here indicates that gravitational force always acts in a downward direction with respect to the Earth. I release a pen and it drops down. Therefore, its direction is downwards. Therefore, it is represented as negative. Now, gravitational potential energy is the energy taken to do the amount of work done in gravitational potential. Now that is represented by U, and it has the formula minus G capital M small m divided by R. Now with respect to the Earth, and G stands for the constant, capital M stands for the mass of the Earth, small m stands for the mass of the object, and R stands for radius of the Earth. Now let's move on to the next topic. Satellites. From one corner of the mind map to another. Let's expand satellites. Now, the definition for satellites is that they are heavenly objects that revolve around a planet. Now, satellites usually have an elliptical orbit around a planet or a circular orbit. Now, the Earth's natural satellite is the moon, and we have been sending artificial satellites since 1957. Now, in satellites, we'll be learning about polar satellites, geostationary satellites, weightlessness, and formulae regarding escape speed and orbital speed. Let's move to escape speed and orbital speed and find out their formulae. This is the section, and here it is expanded. Now, these formulae and the values given here are very important because they are asked in your problems regarding gravitation. Now these values, these formulae can be applied anywhere. However, the values such as 11.2 are specific for the Earth. Now, escape speed. What do you mean by escape speed? The speed required to lift an object from the Earth into space and to keep it moving. So it, in reality, escapes the effective gravitational field of the Earth. Now, how do you calculate escape velocity? Now V escape stands for escape velocity, and it is given by the formula 2 capital G m divided by r, the whole root. Now G stands for the constant, m stands for mass of the earth, r stands for the radius, and the whole formula is under a square root. If we write it in terms of acceleration due to gravity, that is the small g, we get the formula escape velocity is equal to the under root of 2gr. G stands for the acceleration due to gravity, r stands for the radius again. Now, for the Earth, the escape velocity is 11.2 kilometers per second. Now, that's a hell lot of a value, and most rockets don't even use this value. This value is used when an object is intended to go into outer space, far away from the Earth's gravitational field. Now, suppose you want to keep a satellite in orbit. You must be having a speed lower than that. Now, the speed at which a particle is projected from the Earth such that it orbits the Earth is known as orbital speed. Represented by v orbital, it is represented by the formula under root of gr. Now here, the small g stands for acceleration due to gravity, r stands for the radius, and the whole value is under a square root. Now, the relation between orbital speed and escape speed is as follows. Orbital speed is equal to escape speed divided by root 2. So if you have the value of the escape speed, you can easily find the value of the orbital speed by dividing the value by root 2. Now, the next value is the total energy of a satellite. Suppose a satellite is in orbit around the Earth. It has both kinetic energy and gravitational potential energy. To find the total energy of the satellite, you use this simple formula. E is equal to kinetic energy plus potential energy. Now, the kinetic energy of a satellite would be gmm divided by 2r. And the potential energy, which is found in gravitational potential energy, is minus gmm divided by r. Again, the capital G stands for the constant, 6.67 into 10 raised to minus 11. The capital M is the mass of the Earth, the small m is the mass of the satellite, and r is the radius of the orbit. Now, the final formula when you add these two will be minus half gmm divided by r. Now, again, those values still hold. The capital M is still for the mass of the Earth, and the small m is still for the mass of the orbit, mass of the orbiting satellite. Now, these formulae and values are pretty important, and I hope you remember them as we move on to the next topic, which is geostationary and polar satellite. Now, what do you mean by a geostationary satellite? Geostationary satellite is a satellite which moves at the top of the equator at the same speed as the rotation of the Earth, and it is usually used for communication purposes. Now, a geostationary satellite appears relatively stationary to the orbit of the Earth, but in reality, it is moving at the same speed as that of the Earth's rotation. Therefore, we call it a geostationary satellite. Now, since it's stationary, it can access a wide area of people on land, and therefore it's used for communications such as the internet, GPS, etc. Now, here are some facts which are pretty important for a geostationary satellite. The height of a geostationary satellite from the surface of the Earth is 36,000 kilometers. It's 36,000 kilometers above the surface of the Earth. The radius of orbit of a geostationary satellite is 42,400 kilometers. The time period of a geostationary satellite is 24 hours, which makes it appear relatively stationary to us. Now, the orbital velocity of a geostationary satellite is immense. It is 3.1 kilometers per second. However, that pales in comparison to the other satellite that we are about to learn, polar satellites. Polar satellites are satellites which have an orbit which goes from north to south and back to north and back to south. Now they cover a very few slice of the Earth, but the Earth is still moving, and therefore their unique orbit allows them to map out the Earth. So they're used for mapping purposes. The height of a polar satellite is less than that of a geostationary satellite, only 880 kilometers above the surface of the Earth. May be small in comparison to geostationary satellites, but is still large by our standards. The time period of a polar satellite is 84 minutes. That's about 1.5 hours. How fast? Now wait till you see the orbital velocity of a polar satellite. It is 7.92 kilometers per second. That is a very huge number, even when you compare it with the orbital velocity of a geostationary satellite. Now, I hope you've enjoyed geostationary and polar satellites. Let's move on to the next topic, that is weightlessness. The definition here states that during free fall under gravity inside a spacecraft or satellite, a body is weightless. That is, effective weight becomes zero. Now, in our measurements, we use the normal reaction to find out our weight. Now, the normal reaction on Earth, on a solid surface which is not moving, will be equal to the weight, mg. However, as the surface of the body, the surface of the object and the body are moving down at the same speed during free fall, they don't even measure the normal reaction. There is no normal reaction. Therefore, the body is effectively weightless. Now, satellites in orbit actually are in free fall, but do you know why they don't crash into the Earth? They have a huge orbital velocity, and that velocity helps them to stay in orbit without falling down. So they still have free fall, but because of their speed, they don't fall down like Newton's apple. And that completes the chapter. I hope this mind map made things simpler for your boards and to some extent for your NEET and JEE exams. Share your views and suggestions in the comment section below. We will be happy to look into them and improve ourselves. Please don't forget to subscribe to our channel, Brain Blitz Audios, for receiving great content such as stories, poems, mind maps, etc. Please like the video and support us in this quest. See you soon. Goodbye.